According to the National Electrical Code, secondary protection is not always explicitly required for a transformer installation. In the specific scenario of a 45 kVA transformer with a 240 volt delta primary connected to a 120/208 volt Y secondary protected by a 125 amp primary breaker, the NEC may not mandate secondary overcurrent protection directly at the transformer. However, this does not negate the importance of proper overcurrent protection on the secondary side to protect the transformer itself, the secondary conductors, and downstream equipment. The decision to install secondary protection and the sizing of that protection involve several considerations based on NEC guidelines and best practices. Firstly, consider the transformer's full load current on both the primary and secondary sides. The primary full load current can be approximated by dividing the transformer's kVA rating by the primary voltage and then adjusting for the square root of 3 if it is a three-phase system. In this case, 45 kVA converted to volt amps is 45,000 volt amps. Divide that by the primary voltage of 240 volts, and then divide that result by the square root of 3, approximately 1.732. The result is around 108.25 amps. The primary breaker size of 125 amps exceeds this calculated full load current. This is allowed within certain NEC guidelines as the primary overcurrent device is primarily intended to protect the primary conductors and the transformer itself from internal faults. The secondary full load current is calculated similarly, dividing the 45,000 volt amps by the secondary voltage of 208 volts and dividing the result by the square root of 3. This gives approximately 125 amps. Secondly, examine the NEC transformer protection requirements. NEC Section 450 covers transformers. The specific rules for overcurrent protection depend on several factors, including the transformer's impedance and whether it is supervised. If the primary overcurrent protection is sized according to NEC tables and is intended to protect the transformer, then additional secondary protection might seem redundant from a strict code compliance standpoint. However, the NEC is a minimum standard, and good engineering practice often dictates more robust protection schemes. The common practice of providing secondary protection stems from a desire to protect the secondary conductors from overloads and short circuits, as well as to provide an additional layer of protection for the transformer itself. Thirdly, consider the tap rules. The tap rules, found in NEC Section 240.21, allow conductors to be tapped from a main feeder without overcurrent protection at the tap point, provided certain conditions are met. These conditions include limitations on the length of the tap conductors, their ampacity relative to the overcurrent device protecting the main feeder, and the presence of overcurrent protection at the load end of the tap. In the scenario described, where the secondary panel is located 100 feet away, the tap rules could potentially be invoked if the secondary conductors meet the requirements for length and ampacity. However, even if the tap rules are satisfied, installing a 150 amp breaker at the secondary panel offers enhanced protection. The 150 amp breaker at the secondary panel is permissible if the secondary conductors are rated to carry at least 125 amps, which is the transformer's calculated full load current. Furthermore, the 150 amp breaker protects the conductors from overload and short circuit conditions, and also provides a convenient means of disconnecting the secondary circuit for maintenance or troubleshooting. Fourthly, evaluate the conductor ampacity. The secondary conductors must be sized to carry the calculated full load current of the transformer secondary, which is approximately 125 amps. The NEC provides tables, such as those found in Article 310, that specify the ampacity of conductors based on their size, insulation type, and installation conditions. Factors such as ambient temperature, the number of conductors bundled together, and whether the conductors are installed in conduit or free air all affect their ampacity. It is crucial to select conductors with an ampacity sufficient to carry the 125 amps continuous load, with appropriate directing factors applied as necessary. If the conductors are rated for at least 125 amps and the 150 amp breaker does not exceed the conductor's allowable ampacity after dirting, then the installation is code compliant from a conductor protection perspective. Fifthly, discuss the overcurrent protection. The overcurrent protection device, whether a fuse or a circuit breaker, must be sized to protect the conductors from overloads and short circuits. The NEC specifies maximum overcurrent protection ratings for conductors based on their ampacity. In general, the overcurrent device should not exceed the conductor's ampacity unless specific exceptions apply. These exceptions might allow the NEC standard size overcurrent device to be used if the conductor ampacity does not correspond exactly to a standard breaker size. However, it is always best practice to select an overcurrent device that is as close as possible to the conductor's ampacity without exceeding it. In this case, the 150 amp breaker is suitable if the conductors are rated to carry at least 125 amps, and the derated ampacity is still above 150 amps. Sixthly, analyze the short circuit current. A short circuit study is essential to determine the available fault current at the secondary panel. This study involves calculating the impedance of the transformer, the secondary conductors, and any other components in the circuit to determine the maximum current that would flow during a short circuit condition. The overcurrent protection devices must have an interrupting rating sufficient to safely interrupt the available fault current. If the available fault current exceeds the interrupting rating of the breaker, a catastrophic failure could occur during a short circuit. Therefore, it is crucial to select breakers with an appropriate interrupting rating based on the calculated fault current. Seventhly, consider voltage drop. Over a distance of 100 feet, voltage drop can become a significant concern, especially under heavy load conditions. Excessive voltage drop can cause equipment malfunction, reduced efficiency, and potential overheating. The NEC recommends limiting voltage drop to a certain percentage of the supply voltage, typically 3% for feeders and 5% for branch circuits. To minimize voltage drop, it may be necessary to increase the size of the secondary conductors beyond what is required for ampacity considerations alone. Voltage drop calculations should be performed to ensure that the voltage at the secondary panel remains within acceptable limits under full load conditions. These calculations take into account the conductor's length, current, and resistance, as well as the power factor of the load. Eighthly, examine the coordination and selective coordination. Coordination refers to the process of selecting overcurrent protection devices such that a fault on a branch circuit will cause only the branch circuit breaker to trip without tripping upstream breakers. Selective coordination is a more stringent requirement where the overcurrent devices are coordinated under all fault conditions. Selective coordination is often required in critical applications where a power outage could have significant consequences. Achieving coordination and selective coordination requires careful selection of overcurrent devices with appropriate time current characteristics. The goal is to ensure that the downstream breaker trips faster than the upstream breaker, isolating the fault and minimizing the extent of the outage. Ninthly, document the installation. Proper documentation is essential for any electrical installation. This documentation should include a detailed single-line diagram showing the transformer, overcurrent protection devices, conductors, and connected loads. It should also include calculations for conductor ampacity, voltage drop, and fault current. The documentation should be kept in a readily accessible location and should be updated whenever changes are made to the electrical system. This documentation is valuable for troubleshooting, maintenance, and future modifications to the electrical system. Tenthly, emphasize the importance of consulting a qualified electrician. Electrical installations can be dangerous, and it is essential to consult with a qualified electrician to ensure that the installation is properly designed and installed in accordance with all applicable codes and standards. A qualified electrician has the knowledge, skills, and experience to perform the necessary calculations, select appropriate equipment, and ensure that the installation is safe and reliable. Furthermore, a qualified electrician can identify potential hazards and recommend solutions to mitigate those hazards. Engaging a qualified electrician is an investment in safety and reliability. The electrician must follow safety practices when working on electrical equipment. Firstly, always energize the circuit. Secondly, verify the circuit is de-energized. Thirdly, use properly rated personal protective equipment. Fourthly, maintain a safe work distance. Fifthly, inspect tools and equipment. Sixthly, follow lockout-tagout procedures. Seventhly, be aware of surroundings. Eighthly, do not work alone. Ninthly, plan the work. Tenthly, focus on the task.